all of Francisco, student at ICNC, who's talking about curves in Minkowski and very geometry.
Thank you. Good morning. I would like to thank the organized committee by this opportunity and to say happy birthday to Frederico. Now I speak a little bit about my PhD thesis works, that is about the curves in the Minkowski plane and their geometry. Let's go then. The problem. What is the problem that motivated our work? The problem is to find a theory that explains the formations of singularities of a curve in the Minkowski plane, as well as the changes in its geometry. For example, here we have a figure in the Euclidean case of a one-parameter deformation of a cusp curve. Okay? Here we note that in one side of the transition we have one inflection point and one self-intersection point. And on the other side of the transition we have three inflection points and two vertices. Okay? There are some works on this problem for the Euclidean case. We mentioned here in 1983 David did a classification of certain types of plane curves which are given by the projection of a space curve. Okay? And they did a classification by the A equivalence. The equivalence relation by the group A is very important for studying singularities of map geoms. But if we are interested in the geometry of curves, this relation is not very appropriate, since the diffeomorphism do not preserve its geometry. Okay? Then we mention here another works by Diaz, Nuno Ballesteros, Ossat-Signatari, and Wall. These works handle with a single curve, not a family of curves. Then this problem here for the Minkowski plane and the Euclidean plane is still an open problem. But in 2017, Salarino Gabintari proposed a way to study the formations of plane curves that take into consideration the geometry of the curve as well as their singularities. They call this method by FRS the formations of plane curves. In my work, we consider the same questions, but for the Minkowski plane. Let us see. The Minkowski plane. What is the Minkowski plane? The Minkowski plane is denoted by R12, is the plane endowed with the pseudo-scalar product given by this expression. Okay? Here, any non-zero vector has three types of vectors here. If the product of this vector and itself is positive, we call it a space-like vector. If the product is zero, we call it a light-like vector. And if it's negative, a time-like. Okay. What is an inflection point here? Okay. Here we want to study the geometry of curves. And what is the differential geometry here in the Minkowski plane? Okay. If you have a smooth and regular curve in the Minkowski plane, and then away from light-like points, we can define a unit tangent vector, given by this way. We note that in the same way in the Euclidean plane. And we define the unit normal vector, given by this way, where the sign plus happens when the curve is time-like, and the sign minus happens when the curve is space-like. This symbol here represents the orthogonal vector, which can be obtained by changing the coordinates. Okay? And geometrically, the meaning of the orthogonality here in the Minkowski plane changes a little bit. For example, if we have this vector, non-zero vector, and non-light-like vector, this blue vector here, its orthogonal vector, this red here, can be obtained by a reflection by the diagonal line. Okay? And here, for example, if we have a light-like vector, for example 1, 1, then its orthogonal vector is itself. Okay? And we can define a curvature function by this way. We observe that we define here away from light-like point. It is important information. And now, what is about the inflection points? Here we define inflection points by using the contact of the curve with lines. Okay? Then the contact of a curve with lines is captured by the singularities of a high function, given by this way. And then we call the point an inflection point if the curve has a contact of order greater or equal to 2 with its tangent line. Okay? Then we have some kinds of inflection points here. The first one, if the contact is exactly of order 2 and the point is not light-like point, we call it an ordinary inflection point. If the point is light-like, a light-like ordinary inflection point. If the contact is of order k plus 1, then an inflection point of order k, if the point is not light-like. If it's light-like, we define a light-like, we say light-like inflection point of order k. Okay? Here we observe that we define the inflection points without using the curvature function. But away from light-like points, we can see that the inflection points is the zeros of the curvature function. Okay? Now we define the vertices. Here we don't define the vertices by the contact with pseudocircles, because if we are in at a light-like point, because if we are in a light-like point, the distance square function can have different types of singularities. If the center, in this case, the pseudocircles is a line, and then the center can be the origin or not. If you are not the origin, the distance square function has some type of singularities, and if it is the origin, the singularities is more degenerate, is greater order. Okay. And then here we define a vertex only for space-like and time-like curves as the zeros of the derivative of the curvature function. Here we also have two kinds of vertex, an ordinary vertex if this is satisfied, and a vertex of order k if this is satisfied. Okay? We have an important object related to vertices, that is the evolute. Here we define the evolute away from light-like points, okay, as this curve. Okay? We observe here that the evolute depends on the curvature function, and the curvature function is not defined on the light-like points. Then here we don't have a definition of the evolute in the light-like points also. Okay? But we have a more general concept that include the light-like points, that is the caustic. The caustic of a curve in the Minkowski plane is the bifurcation set of the family of distance square function, where the distance square function is given by this one. Okay? We observe that away from light-like points, the caustic of gamma and the evolute is the same thing. Okay? Now we will see some important examples of the behavior of the caustic in special points. What special points? First one is an ordinary vertex, a vertex of order 2, and an ordinary inflection point. Okay? Let's go there. First one, for the behavior of the evolute in an ordinary vertex is given by this figure. Okay? Then we have two types of configuration of the evolute. Okay? How can I identify what of these is happen? We analyze the sign of the product of the curve, of the curvature function, and the second derivative of the curvature function at the vertex. Okay? If the sign is positive, the behavior is like this. If the sign is negative, the behavior is like this. We observe that in this presentation, all evolute and caustics are drawn in a head curve. And the curve is the blue color. Okay? And the vertex are described here by a small square, the inflection point a small ball, and light-like points a small star. Okay? Then, naturally, here we have two kinds of ordinary vertex. And then we can define. We call an ordinary vertex an inward vertex or an outward vertex. An inward vertex happens when the evolute has this configuration. And the outward vertex happens when the evolute has this configuration. Okay? Now, for a vertex of order 2, we can see that the evolute, given this picture here, center, the evolute has a singularity A equivalent to T3, T4. And then, in a generic one-parameter family of curves, the evolute undergoes the swallow-tail transition. That means that in one side we have two ordinary vertex. One is inward and the other is outward. And on the other side we don't have any vertex. Okay? Now, for an ordinary inflection point, we can see that the behavior of the evolute is given by this figure. The evolute goes to infinity asymptotically along the normal line. The two components of the evolute live in the two quadrants which not contain the curve. And the evolute can be modeled by xy equal to 1 in some coordinate system. Okay. In the work of Salerno Gabintari, they call the method by FRS deformations of plane curves. Here we call by FRLS deformations of plane curves. F for flat, R for round, L for light-like, and S for singular. Okay? Let us see what concerns this method. Okay? Then here we have the following situation. Consider two gems of m-parameter deformations, gamma s and alpha r, and we consider also the parameter space of gamma s endowed with a stratification, such that in each stratum all the curves have these three properties. They are diffeomorphic, they have the same number of inflection points, vertices, light-like points, and singularities, and they have the same relative position of their inflection points, vertices, light-like points, singularities, and self-intersection points. And we consider also the parameter space of alpha r endowed with another stratification with the same properties. Okay? Then we say that these two deformations are FRLS equivalents if there exists a germ of homeomorphism between the parameter space of gamma s to the parameter space of alpha r, such that for each s, the curves gamma s and alpha hs has these three properties. Okay? Basically, the FRLS equivalence means that the instantaneous configuration of these two curves, gamma s and alpha h of s, is the same, including their inflection points, vertices, light-like points, singularities, self-intersection points, and also their caustics. Okay? In this work, we study the FRLS deformations of local phenomena with codimension less or equal to 2. Okay? But here we present only for regular curves, and we describe in details these four situations. Okay? The FRL deformations of plane curves at special points, and at an inflection point of order 2, of order 3, and light-like ordinary inflection point, and light-like inflection point of order 2. In each case, we want to define the concept of FRLS generic deformation. The idea is to show that any two FRLS generic deformations are FRLS equivalent. Okay? Let us see. Okay. Now, for the case of regular curves. We know from the classical singularity theory that if you want to study the formations of plane curves at a vertex of a finite order, then it's enough to study the family of distance square function. If it is an R plus Verso deformation, then we have a well understood model. And in the same way, if we want to study the formation of plane curves at an inflection point of finite order, we study the family of height function. If it is an R Verso deformation, we get a model. Okay? But here, we want to study the deformation of plane curves at inflection points of finite order, but taking into account vertex and line-like points that can appear. Okay? We observe also that the distance square function measure the contact with circles. Okay? But at an inflection point, the center of the circle with more contact with the curve goes to infinity. Okay? And then the next result shows a way to study inflection points and vertex without using the distance square function. Okay? Here. Then we have a m-parameter family of regular curve with no light-like points. And then, and suppose that this family has a curve such that that has a inflection point of order greater or equal to 2. And then we have two information here. The first one, the family of height function is an R plus Verso deformation if and only if the family of curvature function is an R Verso deformation. And if the family of curvature function is an R Verso deformation, then the derivative of the curvature function is an R Verso deformation also. Then here we can see that the zeros of the curvature function give us the inflection points, and the zeros of derivatives of the curvature function give us the vertices. Okay? And then this condition for the family of height function being R plus Verso deformation is a good condition, because from that we can study the inflections and vertex simultaneously. Okay? Now then we say that a deformation of a regular curve with no light-like points is FR genetic at an inflection point of finite order if the family of height function is an R plus Verso deformation. Okay? Now we will see the FR genetic deformations at the special points, inflection points of order 2 and inflection points of order 3. Let's go. First, for the inflection points of order 2, we have firstly the behavior of the evolute are given this central figure. Okay? The evolute goes to infinity asymptotically along the normal line. The two components of the evolute live in the two quadrants which not contain the curve. And the evolute can be modeled, by x squared y equal to 1 in some coordinate system. Okay? Secondly, if we consider a FR genetic one-parameter family of curve which contain the original curve, then the bifurcations on the evolute are given by this figure. That means in one side of the transition we have two ordinary inflection points and one outward vertex. And on the other side of the transition, we don't have an inflection point, but we have an inward vertex. Okay? And thirdly, if any FR genetic one-parameter family of curves at an inflection point of order 2 is FR equivalent to this model. Okay? How can I show this? The idea of the proof is the following. The first item, the behavior of the evolute, can be obtained observing that locally at an inflection point of order 2, we can write the curve in this form, where A0 is different from 0. And from that, we can get by a and then conclude the first item. To the second item, we observe that as gamma s is a FR genetic deformation, then we can write it in this form. Okay? And from that, furthermore, we know that the curvature functions of this, the family of curvature functions is an R versal deformation of an A1 singularity. And then we can get the zero and the singular sets of this family and conclude about the bifurcations on the evolute. To prove the third item, it's enough to see that the calculations in the second item depend only on the fact that the curve has an inflection point of order 2 and on the deformations being FR genetic. Okay. Now, in the same way, for the inflection point of order 3, we have firstly the behavior of the evolute are given by this figure 1 here. The evolute goes to infinity asymptotically along the normal line. The two components live in the two quadrants which do not contain the curve and can be modeled by x cubed y equal to 1 in some coordinate system. Okay. Secondly, if we have a FR generic two-parameter family of curves which contain the original curve, then the bifurcations on the evolutes are given by this figure. Okay. We observe here that the bifurcations diagram is composed by a cusp curve corresponding to inflection points of order 2 and a regular curve corresponding to vertex of order 2. And thirdly, any FR generic two-parameter family of curves at an inflection point of order 3 is FR equivalent to this model. The proof of this is in the same way to the previous case. Now we have seen the FRL deformations for outside away from light-like points. And now what happens for light-like points? Okay. Here in this work of Saloon and Tari, they showed that all smooth, regular and closed curve has at least 4 light-like points, and then light-like points can appear always. Okay. Here in this figure, we have an original curve with 1 light-like point, and we can deform it, and here the light-like point goes out, and here we have a birth of another light-like point. And here we can see that a light-like point is a point such that the tangent line is parallel to the diagonal line. Okay? Then it's natural to expect a deformation such that preserves these lines. Okay? Let us see. Here we take the curve and the deformations in this form, with f of 0 and the first derivative of f and 0 is equal to 0. But we want to see this figure and this curve and this deformation by a 0 level of curves of function. Then we consider a function g such that the 0 level is locally the curve. And consider also a deformation big G such that for each s, the 0 level is locally the curve gamma s. Okay? Then we naturally consider the subgroup denoted by K star of the contact group K, where the change of coordinates in the source preserves the diagonal lines. Okay? And then we can say that deformation gamma s is a K star versal deformation of the curve gamma, if these deformations big G is a K star E versal deformations of the small g. Okay? Then we say that deformation gamma s of a regular curve at the light-like inflection point of finite order is FRL generic if gamma s is K star versal deformation. Okay? In the previous case, away from light-like point, we can see naturally why the condition to be FR generic is a good condition. But here is not very clear how this condition can be a good condition. For to see this, we go to the jet space. Okay? For this, we consider Vn, the set of polynomials in one variable of degree at most n, and without constant terms. And then we know that any smooth curve can be written in each point as a graph of function, and then we can define the Monge-Taylor map by this function. Okay? If we have a family of curves, then we have a family of Monge-Taylor maps. And we proved that at a light-like inflection point of finite order, the condition for gamma s being FRL generic is the same condition for the family of Monge-Taylor maps being transversal to the stratum of light-like inflection points and to the stratum of vertex that can appear. Okay? Then it's a good condition. Okay? Now we will see in details the FRL deformations at special points. The first one is a light-like ordinary inflection point, and the second a light-like inflection point of order 2. Then, at a light-like ordinary inflection point, we have firstly the behavior of the caustic are given by this central figure. The caustic is composed by a diagonal line and a regular curve. Secondly, if we have a FRL generic one-parameter family of curves which contains the original curve, then the bifurcations on the caustic are given in this figure. Okay? That means in one side of the transition we have two light-like points and one ordinary inflection point. And the other side of the transition we have two outward vertex and one light-like, one inflection, ordinary inflection point. Okay? And thirdly, any FRL generic one-parameter family of curves at a light-like ordinary inflection point is FRL equivalent to this model. How can I show this? Okay. The idea of the proof, the first item, the behavior of the caustic, is the same idea. It is enough to see that at a light-like ordinary inflection point, the curve can be written in this form. And from this, we can get the expression of the caustic and conclude about this, the behavior. Okay? To the second item, we note that the family of distance square function here is an R plus versal deformation of an A3 singularity. We observe that here we are in the case where the center of the pseudo-circles is the origin. Because if it is not, the caustic is only a regular curve. Okay. And then from this we can see that the big bifurcation set is locally diffeomorphic to the cuspidal edge. Okay. Why the big bifurcation set is very important? Because if we take this projection given this way, for each S, the fiber of this projection gives us the caustic of the curve gamma S. Then we can use the classification of a stable function made in 1976 by Arnold through diffeomorphisms in the source preserving the cuspidal edge. We get that the fibers of P could have three models. Regular, that means all the fibers is a cusp curve, or can be Lips or Biggs transition. However, we study the contact of the big bifurcation set with the zero fiber, and we get that the transition is a big transition as we described in the figure below, the previous figure here. Okay. Now, for the case of light-like inflection points of order 2, we have firstly the behavior of the caustic given in this figure 1 here. Okay. The caustic is composed by the diagonal line counted twice and a regular curve. Okay. Secondly, if we have a FRL generic two-parameter families of curves which contains the original curve, then the bifurcations on the caustic are given by this figure. Okay. We observe that the bifurcations diagram consists of two cusps and one regular curve. Okay. This cusp here corresponded to vertex of order 2, here corresponded to light-like ordinary inflection points, and the regular curve corresponded to to inflection points of order 2. Okay? And thirdly, any FRL genetic two-parameter families of curves at a light-like inflection point of order 2 is FRL equivalent to this model. How can I prove this? Okay? The idea of the proof, the first item, is exactly the same idea of the previous one. To the second item, we observe that here we cannot use the classification of stable maps from R4 to R2 made in 1985 by Bruce and Gibling, because here the projection is not stable. And then how can I proceed? Okay. We proceed as follows. First, we can analyze the deformations with respect to inflections and light-like points. Writing the deformations in this form and observing that the zeros of this family give us the light-like points, and the singular points of this family give us the inflection points. And then we can verify that this family is R and R plus verso deformation, and then obtain the model for its zero and singular sets. Okay. Now, and then we can obtain the bifurcations with respect to light-like and inflection points. For the vertex, we use three things. We use the formations already studied, the description of the stratum of order 2, and the analysis of the number of vertex in each stratum. And then we can conclude that the bifurcations on the caustic are given by this figuring. Okay? Here we have some papers that we used, and muchas gracias. Happy birthday, Frederick.
Any questions, please? Alex, so you have classified all possible transitions of singular points of a curve in the Minkowski plane?
In fact, we classify for the regular curve. For the singular curve is the next step. And we classify all the phenomena with codimension less or equal to 2.
Yes.
We analyze.
And you are planning to study also cusps?
Yes, cusp, Humford cusp, and the singularity in the case of non-light-like points and the light-like points, and see what happened with the caustic and the bifurcations.
Okay.
Thank you.
Any other question? Okay, so let's start.